Ladies and gentlemen, welcome to TSMC's 30th anniversary celebration. My name is Kelly Ramos, and I am your MC for today's panel. And on behalf of TSMC, I would like to extend to you our warmest welcome. We sincerely appreciate your being here to join us on this very special occasion. In a moment, you will be seeing a video that shows TSMC's story and where we've been since then. Thank you, and please enjoy.
Let's go back 30 years ago. The paradigm of the electronics industry was vertical integration, design, manufacturing, and sales all in one. Taiwan's semiconductor industry was beginning at square one and still looking for direction. Dr. Morris Chang, invited by the Taiwan government, arrived to serve as president of the Industrial Technology Research Institute and lend his insight to Taiwan's technology development. Drawing on his knowledge and experience and Taiwan's manufacturing ability, Dr. Chang created the unique, dedicated IC foundry business model. Like every innovation ahead of its time, this unprecedented idea had its doubters. Despite the skeptics and countless other difficulties, after a year of preparation, Taiwan Semiconductor Manufacturing Company was founded in 1987. TSMC's technology has advanced from 2 to 3 generations behind to the forefront of the industry's leading edge. In depth and in breadth, we have the technology to satisfy our customers. By earning the trust of our customers and investors, revenue and market cap have continued to set new records over these 30 years. TSMC's pioneering business model has unleashed the power of innovation, lowering barriers for our customers, enabling their world-changing ideas to become reality and make the world a better place. Never competing with our customers is our starting point for winning customer trust and a foundation for our position today. We have collaborated with partners to provide the tools and building blocks for design success and worked side by side with suppliers to offer the right capacity at the right time. Together with our customers, suppliers, and open innovation platform partners, we are a grand alliance that is an unmatched competitive force in the semiconductor industry. For 30 years, over 10,000 days, TSMC's growth has come from the dedication and effort of countless people. From the management team to each employee, to our valued customers and partners, your support and collaboration is what has made this journey remarkable. Over the last 3 decades, we have created many beautiful innovations together. In the coming decades, our commitment to customers and the world will not change. We will never stop moving forward, helping flashes of inspiration become products that make our lives better. With your support and partnership, we are looking forward to an even more spectacular future.
Thank you. We come now to the highlight of today's event, the panel forum, Semiconductors, the Next 10 Years. I'd now like to invite to the stage our panel moderator, TSMC's chairman, Dr. Morris Chang, and the following panelists: Mr. Jensen Huang, Mr. Steve Mollenkopf, Mr. Vincent Roche, Mr. Simon Segars, Mr. Hock Tan, Mr. Peter Wennink, and Mr. Jeff William. Would you all please proceed to the stage?
First, I want to thank all of you for joining us, coming here to join us in our 30th anniversary celebration. I particularly want to thank the panelists that we have invited for this forum. This is a very distinguished panel, and I will introduce each of them as before each of them speaks. The forum will consist of 2 parts. The first part is the big one. It's about 2 hours. And each panelist will speak for about 10 to 15 minutes on a topic of his own choice, as long as the topic is relevant to our theme, which is semiconductor in the next 10 years. I have given them wide scope. They can speak on technology, they can speak on market, applications, products, on M&A, whatever, as long as it's related to semiconductors the next 10 years. And the panelists are alphabetically arranged. Now, the first one is Jensen Huang. However, he just told me that his slides were not ready yet. So, he would like to defer to a later time. So and he will tell me when his slides are ready. Yeah, I think. So let's start with Steve Mollenkopf. Steve is the CEO of Qualcomm, one of the biggest companies in the semiconductor industry. And Qualcomm, as you know, have been our partner for TSMC partner for a long, long time. Steve, please.
Well, thank you. I will try to be very brief. I think I brought one slide, and it's ready. So we will go through it. This is not it, but this is the intro. First of all, thank you for having us here, and thank you for the long partnership. And incidentally, Qualcomm is 32 years old, and so I thought maybe I'd talk about really just one topic. I think in a panel of this size, maybe just leave you with one topic, which is if you look at our first 30 years as a company, which overlapped very broadly with the first 30 years of TSMC, the main theme was how do we get people connected to each other? And at the beginning, it was voice, and it rapidly moved to getting a connected computer in your pocket. And there's a tremendous amount of economic benefit that was created as a result of those things occurring, and we were obviously a part of that, and as were a lot of other people. But and today now you have, just by the nature of having a connected computer in your pocket, there are a number of new business models, companies that didn't even exist 10 years ago, much less 30 years ago. So, for example, all we really did was we put something that had a data connection and a computer in your pocket with GPS and a camera, and now you have an entire internet ecosystem that didn't exist before. But that's sort of where we are today, which is all we did was connect people to everywhere that they are. But in the next 30 years, and certainly the next 10, there will be a tremendous opportunity as everything gets connected to the cloud. And we are obviously working on that. There are a couple of ramifications that I think are interesting. Everyone talks about how everything's getting connected to the cloud and what will happen. From a semiconductor point of view, and certainly from a company like Qualcomm, we tend to view this as a systems problem. How do you create the underlying technology at scale to allow people to use those technologies in a way that they can focus on the business models that are available because those technologies exist? So sort of at a similar model to what TSMC does, which is you don't have to worry about the semiconductor aspect of being a semiconductor company. We try to make it, you don't want to be connected to, or you don't have to worry about the systems aspect of being connected to the cloud everywhere. Now, there'll be huge ramifications, I think, to the way that computing is done. And probably the one that I'm most interested in and looking forward to participating in is as we get the latency down and the computing power up on devices, the ability really for the cloud to become inside out and the smarts to move closer to where the data is actually generated, which is where it's most valuable. And I think there will be implementations and machines that will be created through the platform that TSMC enables that will look very different to what you see today, which today you can kind of think of it as we build central nervous systems. But in the future, we're going to build sort of nerves at the end of your finger that are going to be smarter. And what you have to engineer to do machine learning and smarts and a very low power process to do a low power machine in order to do that will be very different. And so for us, what we're excited about is that we think there are a lot of systems opportunities or systems problems to solve across disciplines. And we think that the big focus of our company, and I think the big focus of at least a portion of the semiconductor industry for the next 10 years, is how do we make that something that everybody in the industry can use without having to be an expert on it. So I think it'll be a very exciting time. In my mind, this is probably the most exciting time to work in the industry, just because everything is going to now need smarts, connected smarts. And that's really what we do as an industry. So I don't think there's ever been a time that this industry is more relevant to the big problems that will be solved in the next 10 years. But that's our one thought. I look forward to hearing from the rest of the panelists, and thank you, Dr. Chang.
Well, thank you, Steve, although it's much shorter than I expected.
I can go on for more if you want me to, but I won't.
Well, if you're curious about why I'm wearing this thing, I have attuned to the English channel, and it does help me to hear better. That's the. Oh, I'm sorry. Do I have to repeat what I just said? Anyway, what I first said was that Steve's talk was much shorter than I really wanted it. But we'll wait till later. We'll wait till later for you to remedy that problem, okay?
I've become very good at remedies, actually. I think it's a different meaning, though. It's probably the second meaning.
Yeah. And anyway, the second thing I said was that if you're curious about why I'm wearing this headset, I have it tuned to the English channel. It's not because I don't understand English. It's because that this headset helps me to hear better. Yeah. All right. We'll give you a bye for now, Steve, okay? And the next is Vince Roche. Vince is the CEO of Analog Devices. And Analog Devices has been one of our oldest partners now. I remember that even in the middle to late 90s, we started to do pretty serious business with analog. Vince is actually the third generation CEO that I know at analog. First generation, first was Ray Stater, and then it was Jerry Fishman, and now it's Vince. Vince, please.
Thank you, Dr. Chan. Great introduction. Good afternoon, everybody. It's a great thrill to be here to celebrate TSMC's 30th anniversary. So we're, as our name says, we're an analog company. And our business is all about bridging the world of the physical and the world of the digital. We're a 52-year-old company, so we've had to morph many, many times through different types of technology. And our business is really, in the spaces we've chosen, our business is really about scope rather than scale. Obviously, a certain level of scale is important, but our business is really about scope, having lots of inherent underlying technologies that enable us to address many hundreds of applications. We actually have about 50 or 60,000 customers in our portfolio, and I think about 60,000 product SKUs these days as well. So it's a very, very complex business. And I remember not long after joining ADI in the late 80s, the prognostications were that the analog business was finished. It was all about digital. So, you know, our investors were confused about who we were and whether there was a future or not. But the good news is our business is about developing a very nuanced view of the real world in many different types of applications, developing better information, creating information and data for our customers, data about the real world, data about ourselves. So I think the analog space is a very, very critical bridge for a long time to come. And it won't be replaced because the world will ever be physical. So over that period of time, as I said, we've had to increase our scope by, we moved from, actually we started life as a module company and then acquired some patents for data converters and became the market leader in data conversion technologies. And that brought us into many, many different types of applications. And beyond that, our first interaction with TSMC was in digital signal processing. And that was an interesting situation for ADI because we didn't have the internal CMOS capability, and we had to look at a foundry model. But in our business, there was always a very strong sense that you had to combine the semiconductor process development with the circuit development. So many, many years ago, Ray Stater had the vision with Dr. Chang to attempt to try this foundry model, which has been a tremendous success for us. So we have followed many, many generations, many lithographies, down into 28 nanometer, and we'll certainly move beyond that, particularly in the areas of high-speed signal processing, where we got the benefit of very, very small lithographies. So, you know, I think at the present time there's a bit of confusion in our industry about, is the industry really on an innovation track, or is the industry in a slow growth period that will never recover? And my own sense is that our customers are trying to tackle very, very complex problems. In many ways, our customers are abandoning the world of hardware design, certainly in the analog space. So they need the help that we bring more than ever. And semiconductors, incidentally, if you look at the numbers, we produce $350 to $400 billion worth of revenue collectively. And sitting on top of that is the $4 trillion IT sector. So all the things that are being attempted by the cloud companies, the industrial automation companies, the car companies, it sits very firmly on that foundation of semiconductors. So maybe over time we will introduce new modalities. We're working with carbon nanotubes, for example, at the present time ourselves, trying to build hybrid silicon carbon nanotube technologies for specific sensing applications. But my own sense is that in spite of the prognostications about the end of Moore's Law, certainly it's got challenges. But we'll blow through those challenges, I think, through continuing to push lithographies, but also bringing new techniques into bear. We're using heterogeneous integration at the present time as a company in different applications, and using more and more 3D packaging technologies to help us bring more modalities of innovation beyond the pure lithography game. So my own sense is that, you know, the skills that we have to develop, as I said, there are many, many areas where we develop like 3D and heterogeneous integration, so we're pushing technology along the more than Moore curve and the Moore curve. But also, I think, when you look at the suite of applications we're trying to solve now, more and more things are digitalizing. More and more things, I think, our customers are dealing with exponentially increasing complexity. It's our job to help solve those problems for our customers as best we can. So I think the future is more challenging, and I think one of the big challenges we have as an industry is how to extract the value for the innovation investment that we're putting in. So I think that's an ongoing challenge for us. But the one thing I'm sure about is that the demand for our technology is there. The question is, what type of new techniques do we bring to solving the problems and feeding the supply and digging into the demand available? So I think aside from the technology innovation, more and more we're having to find ways to match the applications and the problems we're trying to solve at the application level with the solutions we're trying to develop. And I think that's one way to deal with the cost issue, where we specialize rather than generalize. And I think as well, on one of the TSMC charts, there was an ecosystem mapped. That's becoming a more critical feature as well, I think, of doing business in this industry. We have to get better at moving beyond the boundaries of our own companies and developing more rich formal and informal partnerships in the ecosystem. And for ADI, for example, software is becoming a problem that we have to grapple with more and more, not just the hardware. So those are just some ideas, I think, in terms of the analog industry, the kind of innovation modes we're working along. And I think, as I said, I don't see a better solution to the problems that the world of information and communications technology is trying to resolve today without semiconductors. So that's pretty much all I have to say, Dr. Chang, at the present time.
Thank you, Vince. Next is Simon Segars. Dr. Simon Segars, the CEO of ARM. And ARM is now a very old partner of TSMC's, but in recent years, you have become a very important partner of TSMC's, as you have become a very important partner for a lot of semiconductor companies. Simon, please.
Great. Thank you, and good afternoon, everyone. It's my pleasure to be here to celebrate this incredible milestone of 30 years. As Dr. Chang said, ARM and TSMC have been partnering for a short period within that. I think I first came to visit TSMC in about 2000. We could see an increasing number of our partners were they had stopped building their own fabs, and they were building wafers with TSMC. And we thought about this internally and thought, well, it would be a really great idea if we could partner together and learn together and trial the manufacture of our latest microprocessor on TSMC's latest process. So we started working together on that. ARM is not quite as old as TSMC. We're about 27 years old. But I can remember the first partners we had did have their own fabs. And I can remember the first time we engaged with somebody who had gone fabless, thinking to myself, this is crazy. You're going to make all these chips and you don't own a fab. How are you possibly going to do that with any degree of efficiency? But clearly it turns out that it was a really good idea, one that was caught on, and we wouldn't be here today without it, let's face it. So in coming here, I was thinking, well, 30 years ago when TSMC was formed, what was I doing? I'd actually just gone to university, having kind of gone through the home computing era and learned about technology and been excited about what computing and electronics could do together. I was at this point in my career where I was taking for granted a lot of technology. I'd grown up in a home with color TV and a telephone, and my parents probably thought I was completely spoiled. Here we are 30 years later with all this technology that Steve was describing, and I look at my kids and I hear everyone saying, our kids take this for granted, they're completely spoiled with the technology. But you think 30 years prior to founding a TSMC, what was going on in 1957? Probably the coolest thing you could own was a vinyl record player for playing 45s, and the Russians had just launched Sputnik, so they kind of started the space age. And you think those advances in kind of 30-year increments, it's just incredible. It's way better than linear. We are on this exponential curve of what technology is doing for us. So when you project yourselves forwards 30 years, if the space age drove the kind of 60s on, and these improvements in semiconductor process that led to improvements in computing and increased density in memory and the ability to store everything, if that's driven the last few years, what's going to drive the next decade, the next 30 years? And I think that's going to be data. We're going to see these tiny devices based on all these transistors that TSMC is going to manufacture for us deployed anywhere and everywhere. We're going to see tiny sensors gathering data from anywhere and everywhere. We're going to process it at the edge. We're going to process it in the network. We're going to process it in the cloud. And that's going to create what I like to think of this kind of globally distributed mega computer that's going to just absorb all this data. It's going to be fed by the world's data. And even today, as people were talking about big data, I think we're really just at a starting point. We're at a starting point of huge data, and quite what we do with it is yet to be determined. I think we could probably talk all day about the opportunities that come from that, and I think they are endless. And they're going to create enormous opportunities for new businesses, new business models, and will be the driver of what probably all of us in this room spend the next period of our careers really worrying about. How do we leverage all of this data? How do we leverage all the technologies that have come about and make the most of it? So I see no end of opportunity there, no end for the deployment of more and more transistors in more and more places. But one thing that could potentially get in the way of that, and one thing that I think as an industry we need to collaborate around, are two issues, and that is security and privacy. Because the kind of security issues you see raised in the press every day right now are about stealing credit card numbers and social security numbers. I think that's going to pale into insignificance compared to the kind of data that could get stolen and misused in the future. And so as we go into this era where data is driving the technology, we've really got to fundamentally rethink how we secure the data, really engage in grown-up discussions about the privacy models around that data, because ultimately what we're trying to do is make technologies that make people's lives better. We often talk about users. Well, those users are actually people, and most people, it turns out, don't have degrees in electronic engineering and computer science and aren't really equipped to deal with today's security problems, let alone those that are coming down the pipe. So I think as an industry, we've got to really think about this, think about how we create a new world that is a lot safer for the kind of citizens that will live within this digital world. We've got to throw away these old models of just making something secure, testing it, and when it leaves the factory, kind of having no further obligation to kind of look after the person using that device. I think that has to change. You can only know that you're secure against the threats that you knew about when you finished testing the product. The problem is that security is a live thing. The security threats are a live thing. And unless we engage in owning the device after it's been shipped, then I think the users, the people who use our products, are going to be at risk. And that's ultimately going to constrain all the benefits that we could have from AI. So this technology is about people. And this data should and can bring a lot of benefits to those people. Now, since we're celebrating 30 years, I thought I'd go and talk to my daughter, and the reason for that is because she's almost exactly 30 years younger than me. And I said to her the other day, okay, what do you want out of technology in the next 30 years? And this is somebody who I think is like surgically attached to her smartphone. The only time she ever puts it down is when she's broken it, and I have to insert a new one in her hands. She's all the time. And I said to her, you know, what do you want? And she said, well, look, you know, millennials don't really want, you know, flying cars and all this stuff that you old people talk about. She's looking at me. You know, what we want is technology that makes everyday life just better. And I thought, okay, good point. You know, flying cars and gadgets, we're kind of on that. But really thinking about how technology improves people's lives, which is what it's there for, is what we ought to be focusing on. So I hope through yet more collaboration, building out this ecosystem even further, we can get focused on those things and make this technology world a safe place for everybody to go and occupy. Thanks a lot.
Thank you. Thank you, Simon. And I was informed just a few minutes ago that Jensen's slides are now ready. So let's get Jensen back in line now. So Jensen, are you ready to talk now?
I was actually expecting
I really haven't.
Gracious introduction.
Excuse me, I haven't introduced you yet. Jensen Huang. Jensen Huang. Jensen Huang is the CEO of NVIDIA. Really a very old friend and partner of TSMC's. I remember that back, I think it was in the middle 90s. It could have been 93, 94 maybe. TSMC was already progressing, and we were on our way to be a $1 billion sales company. And in 92, 93, 94, we were maybe about few $100 million. And I got a letter in Hsinchu from a person who called himself Jensen Huang. And he said that I'm interested in talking to you about foundry business. So will you please give me a call? So the next time I went to the U.S., I called Jensen. And on the phone, I heard Jensen saying at the other end, there was a lot of noise, you know. Apparently there was a group of people talking there. And I heard Jensen, after after I introduced myself, I heard Jensen say, "Hush! Quiet! Morris Chang is calling me." And that started our business. That started our partnership. And has been about, more than 25 years now. And now, NVIDIA recently, the stock has done awfully well, has gone up 5 or 6 times in 1 year. And it's supposed to be very good at AI. So Jensen, tell us more about it. Or anything else.
Morris, first of all, the reason why I had to write you a letter was because I called your U.S. sales office repeatedly with no success. Because your salespeople were out calling on real customers.
Well, I'm very glad that the current U.S. manager was not there at that time. Okay.
And just put it on record, the reason why my slides were late was apparently I was the only person that prepared. Our performance today is graded. After all these years, like all of you in the audience, we all work really super hard every time that Morris asked to meet to impress him, and so hopefully today I'll say something smart. Also, when Morris and I first met, it was 1993, 1994. I was in my early 30s, and I was talking to Morris today that he was only several years older than I am now. Then. But we got along just fine. He's got a great sense of humor. So let me talk to you about what I'm going to talk to you about. The computer industry has gone through a lot of changes over the years, and in each one of the eras of computing, there were some fundamental forces at work, and the fundamental forces that were at work typically appeared on two sides of the computing stack. On the one hand, how is computation done? And on the other extreme, how is software developed? And usually, one of those two ends of computing would be changing at a time. And if you go back and think about how PC and the mobile and the cloud era has evolved, that is surely true. For the first time in the computer industry, and I've been in the computer industry for quite a long time now, for the very, very first time, two fundamental forces, one in software and one in computing, are simultaneously governing the future of this industry. The first is the discovery of a new form of computing, a new form of developing software called deep learning. Deep learning is on its surface rather simple to understand. It's otherwise called an artificial neural network. Basically a large system of multivariable, high dimensionality linear equations. And it has millions and millions, hundreds of millions of parameters. This equation is extraordinarily large, and it's high dimensionality. It's more than 3 dimensions. It's more than 4. It's more than 5. It's extremely high dimensionality. And it has the ability to essentially curve fit against almost any type of equation, any type of condition you can imagine. And its magic is that it can predict the outcome of classify, predict, recognize, insight from very, very complex unstructured data. For example, if you were to take a picture of this room, what it looks like in binary, in ones and zeros, is just a bunch of goobly glob. It doesn't look like, it just looks like noise. But from that noise, deep learning can learn how to recognize insight. Well, deep learning has this incredible ability to automatically write software, essentially. So software is writing software, and for the first time, computers can write software instead of computer scientists writing software. It's one enormous handicap, and the reason why it's taken so long to really become popular is because it requires an enormous amount of data to learn from so that it can recognize the patterns that is existent in the data. And because it requires an enormous amount of data to learn from, and because the equation is so large, this linear system of equations is so large that it requires an enormous amount of computation in order to effectively learn how to predict outcome from the data. The second dynamic that's happening almost at basically the same time, as it turns out, unfortunately, CPU performance is no longer scaling. CPU performance has stalled, what some people describe as the end of Moore's law. Even though the number of transistors we're getting from each and every node continues to grow, the problem is that we no longer know how to take those transistors and transform them into effective computational performance for CPUs. We've essentially run out of ideas. After all of these years, we've tried very deep pipelines. We've tried multi-scalar, basically multi-issuing of instructions. We tried speculative execution, out-of-order execution. We tried basically all the techniques we know how. And we wrung out of the CPU as much performance as we know. As you can see, the white line is transistor progress. As you shrink geometry, the number of transistors continue to grow. And on the blue line, it's basically CPU performance. Now, what's really staggering about this is that CPUs are basically improving by a factor of 5 every 5 years, okay, using that as a simple number. So basically, every 15 years, it increases in performance by a factor of over 100. If we lose that trend, we would have a deficit of 100x in another 10 years. And so 100x in performance at a time when the world has discovered this incredible new software technique would be a real tragedy. These two dynamics, these two are essentially the governing dynamics of the computer industry today. Almost every single software company in the world is trying hard to adopt deep learning because of its incredible effectiveness, and I'll show you some of the results. And then secondarily, we all recognize now betting on the CPU or just riding on the CPU's natural performance curve is no longer an effective way to continue to improve performance. The reason why NVIDIA has been growing so fast is because we pioneered this approach called accelerated computing some time ago. This is almost 15 years ago now. The fundamental business of our company, of NVIDIA, is about creating a computer architecture that accelerates applications that otherwise wouldn't be possible. We accelerate applications that otherwise wouldn't be possible. And the way we went about doing that was adding a processor as a companion processor to the CPU. Instead of replacing the CPU, we had the wisdom of offloading the CPU of the work that the CPU wasn't good at doing, where we could do a much, much better job. The architecture of our GPU is fundamentally different than the CPU. The CPU is a sequential processor. We're a parallel processor inherently. The performance results, the benefits, have been extraordinary. And in fact, just this year, the 2 Nobel Prizes, one is called cryogenic electron microscopy, basically using electron beams to image biomolecules. And then the other one is called the Laser Interferometer Gravity Wave Observatory. Basically, two massive arms, two tunnels with lasers that light all the way down the tunnel reflects back in a mirror. And they were able to prove something that Einstein predicted 100 years ago, that gravity had waves. And they detected two black holes colliding in 2015. And they were just awarded the physics Nobel Prize. In both of those examples, the GPU was used as the computational engine for these incredibly high-fidelity imagers. And without the GPU, it surely wouldn't have been possible. And so it's great to be able to contribute to both of these Nobel Prizes. Now let me show you how other people are using it. In industry after industry, whether it's in high-performance computing, in life sciences, in internet services, our GPUs are now used for everything from voice detection, speech. When you converse with your phone, the GPUs are used to train the neural networks used to recognize your voice, to high-performance computing to discover new drugs. But let me show you a couple of examples. I made a couple of home movies for you. And in this case, the first one I'm going to show you, and Simon, I got to talk to your daughter. I think flying cars are way cool. As you know, we finally figured out that one of the most important technologies necessary to enable self-driving cars. In order to create self-driving cars, the fundamental problem is perception. The car has to be able to recognize what's happening around the car and determine what to do. First of all, perceive the surroundings. Second, reason about where it is relative to the world. And third, make a decision about how to drive. Perception, reasoning, and planning are the three fundamental actions and functions of robots, artificial intelligence agents. And for the very first time, we've been able to solve those problems because of deep learning. And with GPU acceleration, I'm going to show you some of these results. This is a homemade movie that gives you a sense of what's now possible. Running this neural network, and the neural network looks at all of these pixels on the screen and automatically recognizes what's a truck, what's a car. The reason why they have segments, the distance from the car. Just imagine this video, the car is looking at this video. These are the neurons that's inside the car, inside the brain of the artificial network. This is the car seeing everything around it, surround perception. It doesn't matter what the orientation of the car is, it recognizes it as you drive by it. It recognizes people, signs, lights. Imagine what the car ultimately sees is a bunch of ones and zeros. It recognizes cars, but it also recognizes where it's safe to drive. It's called safe space. It processes LiDAR, which is a bunch of point clouds. It figures out where it's at. It's called ego motion, visual odometry. It figures out where it's at relative to an HD map, compares itself to an HD map, uses the LiDAR to figure out where it's at. So it's perceived the surroundings, it's figured out where it's at, figures out where it's at in the map, and now it's got to plan its path. It's got a bunch of choices to choose from, and it chooses the safest, the best ones. Comes up to a cross traffic, looks side by side, and makes a hard left. artificial intelligence, self-driving cars. Okay, I'm going to show you one more example of what artificial intelligence can do. The artificial neural networks is at some level an extremely complex concept, at some level relatively easy. But the question is now, how do we turn this incredible new technology called deep learning into something that ultimately reflects our ultimate version of intelligence, which is autonomous characters. The example I'm going to show you here is called Isaac. You're looking at a screenshot of the world that Isaac is currently living in. And here what we're going to do is try to teach Isaac how to putt. And the way to think about putting is you've got to pick up the club. You've got to figure out how to strike the ball, where to strike the ball. You have to read the green, because as you know, the green has slope. And you got to figure out how hard to hit the ball, eventually landing it in the puck, in the cup. So the question is, what's the methodology for doing that? We're using a technology here called deep reinforcement learning, basically the same way that we learn as children. We try again. And every time we fail, we're, punished. And every time we succeed on a random basis, we get rewarded. And over time, it worked towards the goal. Okay, so I'm going to show you a whole movie here of Isaac learning how to putt. There's a slope on the green. This is how Isaac started, is try to see where is the ball? Where's the cup? How do I swing this club? And he accidentally strikes it. That's good. Now do it the same way next time. And now it figured it out. Look at this. The ball's obeying the laws of gravity. Ladies and gentlemen, artificial intelligence. And so, of course, what you're seeing there is a virtual world that obeys the laws of physics, where Isaac can see the world and it's completely photorealistic. And our goal is that eventually we'll take the trained brain of Isaac and put it into a real robot, put him on a real green, and technically, theoretically speaking, Isaac should be able to putt. And this looks like a little bit like a toy right now, but as you know, the beginning of the personal computer industry started out as a toy. In many of these revolutions, the early examples of what's possible is toy-like. But if you could extrapolate into the future and imagine how good it can be, the type of problems that we can solve with it. Once we can solve this problem, obviously manufacturing robots will be highly automated. Surgical robots will be highly automated. The way we farm, the way we do construction, the things that are dangerous to people could be now replaced by robots. It's very clear now that this is the era of AI. I'm sure all of you have been hearing about the power of AI and industry after industry investing in AI. I think that at the highest level, the reason why I think it's so incredible is this. If farming is the automation of food, and the Industrial Revolution was the automation of power, AI is the automation of automation. And this is now the era where computers can learn by itself, software could develop software by itself. The potentials are really quite amazing. And as I showed you just now, the two examples that I've demonstrated are actually software that no human knows how to write. To imagine that there's actually software that no human can write, but a computer can, is really quite a truly remarkable thing. And so I think these are the exciting times. I made a birthday card for you, Morris. To Morris Chang and TSMC in celebration of TSMC's 30th birthday, Morris Chang's extraordinary career, and our lifelong partnership. Happy birthday from all of us.
Thank you.
And I can say that if not for you, these are all the things that you helped us make. If not for you, one of the most touching things that anybody's ever said to me, Morris, was a researcher who came up to me and said, Jensen, because of your work, I can do my life's work in my lifetime because of how we accelerated quantum chemistry for him. And I can say with complete certainty that because of your work, we can do our life's work. So thank you very much.
Thank you very much. Thank you. Thank you, Jensen. Now we get back to the line again. The next is Hock Tan. Hock Tan, the CEO of Broadcom Limited. Actually, our partnership with Hock Tan's organization actually dated back to before Broadcom. It dates back to the old Broadcom, of course, Avago, that Hock Tan was the CEO of, and even before Avago, LSI Logic, and the company that went back to Bell Labs. Huh?
Integrated Circuit Systems.
Oh, yeah. Mm-hmm. Anyway, now, Hock and I also share something else in common. That is that he and I are both bachelor and masters of mechanical engineering from MIT. Same major, same degrees, same school.
Different times.
Different times. He was a class of, he told me this morning that he was class of 75.
Yes.
And I was class of 52. Okay. Okay, Hock, please.
Thank you, Mr. Chairman, distinguished guests. In the presence of this technological insights I've been imbibing so far today, it's with some trepidation that I'm offering to share some thoughts on where our industry, the semiconductor industry, is headed. By the way, for logistics purposes, I'm doing a series of slides. Okay, so you're better off twisting your arm muscles to look at the screen than look at me. So let's start. As with most things, the story begins with demand, as most things in semiconductor. Looking back over 40 years span, you see an industry that grows in the 80s, 90s at over 30% every year. And today it grows at less than 5% a year, basically GDP rate. Okay? And if you look at the slide below, as in any gold rush, the semiconductor industry delivered to early investors alpha returns, very high returns, as you say, above normal S&P 500. But however, last 10 years, the returns have regressed to mean performance. In other words, the gold rush, as we know it, is over. Structurally, this industry has evolved very interestingly. In the 80s, was startups, small startups. In the 90s, we have IPOs and small tucked-in strategic M&A, mergers and acquisitions, as we call it. Then in the 2000s, there was a frenzy of carve-outs from large OEMs who had built up semiconductor capability within them. So there was a frenzy of carve-outs, leverage buyouts, which kind of obscure the fact that the industry is slowing down. And for the last 5, maybe 10 years, we've seen those horizontal mega deals, as we call them, consolidation, as you like to call it. But just because the gold rush is over does not mean we cannot make a lot of money. And a case in point, I can't resist this, Broadcom. Look, that's the Broadcom revenue trajectory over the last 10 years. And if you look closely at the first 5 years, I'll be honest, there's some growth, but we struggle mightily in this very competitive, hostile environment to just even eke out that level of growth. Then, in 2013, the light bulb strikes, turns on, so to speak. Basically, we went out there and started acquiring all those great businesses that we see out there in semiconductors. And there are lots of them. It's a target-rich environment. It also could not have been possible without their support, help, leverage on that, on a strong, enhanced partnership with TSMC. And you can see the last 5 years as history. As far as TSMC is concerned, they didn't do too badly too. It was a very great partnership. But this is a walk down memory lane, I know, to you guys. And no walk down that memory lane is complete without, let's take a look at the ecosystem, the semiconductor or the technology ecosystem as we see it. Nothing is moving. All right, sorry. So, you see it there as an inverted pyramid, pre-1987. I pick 87 for good reason. You probably figured it out sooner or later. It was the dark ages. OEMs, huge OEMs, ruled the earth. They support fragmented demand from enterprises and consumers. Then in the 90s, light shines, driven by mega trends from PCs and later on mobility. Okay, semiconductor industry grew and grew very fast. Innovation was rife, and that innovation drove an interesting phenomenon, which is foundries. Foundries recognize, the emergence of foundries, I should say, recognize the distinction between product design and intellectual property and process. And starts the emergence of foundry business as well as semiconductor growth. Then in the 2000s, data centers started happening, and that continued to drive semiconductor growth, albeit at a reduced rate. But what's also interesting is foundries benefited from that era of OEMs carving out all the semiconductor operations of theirs. And finally, the last 5 years or so, you basically see as the industry in the semiconductor demand slows down to GDP levels, horizontal consolidation occurs. The mega deals happen, as I said. Consolidation happens, supply, hate to say that, stabilize. Foundries gets institutionalized. So we got ourselves somewhat and basic, an optimum, some level of stability. But if you look at demand, things are changing. You see social media driving growth of cloud. You see demand of enterprises manifesting through cloud. So today, you have an ecosystem that sits, as I say, where cloud is almost, spending on cloud is virtually half of total IT spending up there. So what's next? And here's how I see it. Very likely scenario, vertical integration. Cloud operators have reached scale unprecedented. They have the scale to reach down vertically in our ecosystem stack. They have talent to do systems architecture. They write their own operating software. Do they need OEMs? More than that, they can do the chips. They have the capability to draw talented engineers, design engineers in silicon. Do they need design IP sector? Now, going down one step further in the stack to foundries or to silicon production, that the financial requirements might give them some pause. But I doubt it, unless we see the foundries reaching up vertically. Thank you.
Thank you. Thank you, Hock. Next is Peter Wennink, the CEO of ASML. Actually, ASML shares quite a few things in common with TSMC. First, we're about the same age. ASML started them, 1 or 2 years within when we started them. I think ASML started 1 or 2 years before we started them, yes. The second commonality is that Philips was the major investor in ASML when it started. And Philips was the second largest investor in us when we started. And our partnership dated way back to the time we started it. Actually, Philips suggested to us that we buy from ASML. And ASML was, of course, happy to accommodate. And we bought, ever since we started, I think ASML was almost the sole source of our immersion tools, no, not just immersion tools, lithographic tools for all these 30 years. Now, Peter, please.
Thank you, Morris. When you asked me to say a few words, I was humbled because we're a supplier and we do our best. But then, indeed, when I looked back and said what constitutes the relationship between TSMC and ASML, it is partnership, and you already mentioned this. And And I think when you ask me to look forward the next 10 years, of course I'm going to say something about scaling. But I think it's increasingly important that we realize that we need a different level of partnership for innovation because things are not getting easier. And this is what I want to talk about. So, yes, our industry, I think, is very well positioned to tackle some of these big challenges that we're seeing in front of us. And everybody knows it, whether it's sustainable energy or it's the food and water supply or the aging population or the massive urbanization that we will see coming at us. Our industry is very well positioned to do this. And have we been successful in finding solutions? I think we have. And have we been able to create value? I think we have. And just looking back a bit, this industry, if you look at this industry and say, well, this industry constitutes of, let's say, start with the semiconductor equipment manufacturers and then semiconductor design companies and the manufacturing companies going to hardware and then services. If you look at that entire ecosystem has a earnings potential of this year close to $300 billion of EBIT. That's massive. And it means that there is such an enormous amount of value that is out there, and the research and development capabilities are massive. So we're very well positioned to take advantage of our position, but also help these big societal challenges. And what has driven this industry? Scaling. Scaling has actually helped us a lot, and Jensen showed a clear chart where it was also very much going up together with the CPU power. So scaling has helped us, tremendously. We're currently able to increase transistor density. We're at levels where we're over 100 million transistors per square millimeter, and that has been driven by scaling. So when we think about scaling and you think about ASML, you basically say there's one level of scaling. It's geometrical scaling, basically shrinking through pattern and design optimization. But that's not the way how we see the world. I mean, there's different types of scaling that actually help us to get to the point where we want to be. It's device scaling, and in fact, if we want to make this as a bit more simple, device scaling went from planar to FinFETs and to nanowires, and we used from a geometrical scaling point of view, we designed lithographic equipment which went from I-line to ultimately EUV. We'll talk a little bit about that later. But we also need the circuit scaling. We went from individual ICs to a very wide variety of chip types, and the architecture scaling is just as important. Went from general purpose processors to more dedicated silicon. But all these four things, they do not happen independently. They have to be combined. And actually means that we need to work together very closely with our customers to understand the impact of these different scaling types on what we're doing. And even in geometrical scaling, I mean, we need the support and the help of our industry partners that are doing deposition and etch and all the other steps. Sometimes when you talk to the financial world, they try to polarize, who gets what, who wins and who loses, which basically is ridiculous. We definitely need all of it. We need to partner even more strongly than we did before because things are getting more complex. Now, and when you talk about complexity and you look into the rear view mirror, you think that everything was easy when we look back. Well, it wasn't the case. I mean, when we look back and where we are today, we went through big challenges also. And some of those challenges at that time looked like were very difficult to overcome, but we did overcome them. And we did it by working together. I couldn't help resisting looking back when Morris asked me, why don't you talk about the future? I said, I want to also look back in history because history tells you a lot about what the future might potentially bring. Now, the first step, and you mentioned it, Morris, 28 years ago, we shipped the first machine to TSMC. And I asked our people, where is that machine? Because I know that 97% of all our machines are still working. Now, this particular machine, the first one that we ever shipped, is still at TSMC although it donated its parts to other machines of that same generation. But the others are still working. I'm just saying this because over the last 28 years, we've done some incredible things. And I think it was due to this partnership. Now, when we now look at today, we've moved from 0.8 micron now to single nanometers. We went from G-line to EUV. And EUV, as we all know, has been a rough ride until a couple of years ago. And we've made a lot of progress. So what will EUV bring us? Well, EUV bring us over in the foreseeable future, it's 1 billion transistors per square millimeter. And we think about 2030 and we think, what can EUV do? What can the next generation EUV do? Can even go beyond that. And then if we look forward over the next 10 years and see what are the challenges that we have overcome, you might remember the first immersion tools that we shipped to TSMC, which basically were tools that didn't perform that well when we had the first tools out there. But with the help of TSMC and the other partners, we made it a very reliable tool. And is, in fact, the workhorse of the industry today and has enabled us to start doing multiple patterning that we needed as a bridge solution because EUV was not really ready. And we could have only done that because there was such a close cooperation and sharing. And now we're at the age of extreme ultraviolet, EUV. And we're smack in the middle of the preparation of the volume production. And it's going to happen because EUV will add simplification, it will shorten R&D cycle time, it will reduce work in process. In other words, it will do what Moore's law is, which is an empirical law of economics. It will reduce cost. And we've started last year and the year before the basic research into the next level of EUV, high NA, and it will happen. We have the optical designs. We know what to do. We will use the same EUV source. High NA is there to help us in the second half of the next decade. It will bring us beyond 2030. So from a scaling point of view, we have the instruments, we have the equipment, but what we need is our partnership. And, there are always bumps in the roads, and that's why I said earlier, when we look back, in the rear view mirror, everything looks fine. But at that time, we did have our issues, and we overcame them. Just like it was a long road to make EUV a production worthy tool, and especially the last couple of years, we've made huge progress. And that has been the case because we have the partnership. And I think I want to highlight 4 of the basic components of the partnership that we have with TSMC. And I think this we would like to extend, and we are extending to other industry partners also. And it's all about building partnership based on trust. And that's not an old-fashioned thing. Trust is real. We need trust, but first we need, and that's really the 4 pillars of the partnership we have with TSMC. It is competence. I mean, we employ the brightest engineers, and we make them work together. We can do something very, very special. And secondly, it's reliability. As a partner, you need to be very reliable. It means that we are going to tell each other what we're going to do, and we're going to do what we tell each other. And thirdly, I think it's very important, transparency. I mean, when we have to deal with those difficulties and those big challenges, it's extremely important that we are transparent to each other so we understand what needs to be done, what needs to be done now, but also in the next generation machines in 5 years' time and in 10 years' time. And that is not always easy to be transparent, but it's absolutely essential if we want to overcome these big technical issues. And the last, I think probably the most important, we have to manage our self-interest. And especially in the relationship with TSMC, it's about risk and reward sharing. And those 4 building blocks have formed the foundation for us making sure that we can overcome those big challenges. And I'm convinced that where we are today with EUV, with the partnerships that we have a very bright future the next 10 years, and I think together we can make it happen. Thank you, Morris.
Thank you, Peter. Now, last but certainly not the least, by far, far from being the least, is Jeff Williams, Chief Operating Officer of Apple. And our partnership with Apple did not go back very far, but it has been intense, and it's important, certainly very important for TSMC, and I've been told that it's very important for Apple too. Jeff?
Thank you, Dr. Chang. I was going to run through our very detailed product roadmap for the next few years and ask all of you to just keep it amongst us. But like Jensen, I had some slide issues, so I'm just going to ramble on for a few minutes instead. First off, thank you. It's a real honor to be here with this distinguished group, and we're here, of course, to celebrate TSMC's 30 years. It's amazing, as you've seen in the slides, how far technology has been driven over that time. TSMC got its start shortly after the introduction of the Cray 2 supercomputer, legendary Cray 2, and 25 years later, we put the same processing power in people's pockets with an iPhone 4 in 2010. It really is remarkable. And it was actually 2010 that the first seeds of our partnership between Apple and TSMC were planted. I had flown to Taiwan and had dinner with Dr. Chang and Sophie at their house, and it was a wonderful dinner. We were not doing business with TSMC at the time, but we had a great conversation. We talked about the possibilities of doing stuff together, and we knew the possibilities were great if we could take leading edge technology and marry it with our ambitions. And what seems obvious right now wasn't then, because the risk was very substantial. The nature of the way Apple does business is we put all of our energy into our new products, and then we launch them. And if we were to bet heavily on TSMC, there would be no backup plan. You cannot double plan the kind of volumes that we do. We want leading edge technology, but we want it at established technology kind of volumes. And so that may be what Dr. Chang's referring to when he mentions intense. For the TSMC side, it means a huge capital investment, and it means ramping faster than the more careful yield plan that the industry's used to. But together we decided to take the bet, take the leap, and Apple decided, so our first engagement, Apple decided to have 100% of our new iPhone and new iPad chips, application processors, sourced at TSMC. And TSMC invested $9 billion and had 6,000 people working round the clock to bring up a Tainan fab in record 11 months. And in the end, the execution was flawless. And we've gone on together to ship over 500 million chips together in that short window. And I think TSMC's invested $25 billion. $9 billion on that first venture. There are very few companies in the world that spend $9 billion in capital across everything, not a single bet. So for that, we thank you, Dr. Chang, and everybody at TSMC. It's been a wonderful partnership. Now, the request was for me to describe the next 10 years in silicon, which I'm completely incapable of doing. And so I'm going to frame or reframe the question. I think in politics they call this a pivot. But, you know, it's interesting. When we look back a decade ago, the question we had was, do we have enough processing power in our silicon to match our ambitions. The big challenge we had as we moved into the mobile revolution was this trade-off between performance and power. And the view at the time is you had to choose. You've got one or the other. And largely as a result of what the fabless model has done, what TSMC has done, what many people in this room have done, Simon and his organization from ARM, we have reached a point where those trade-offs are not necessary. We have performance in thermally constrained environments. And so this opens up for the next decade a whole new world. So for the next decade, the question is not so much do we have enough processing power to meet our ambitions, though we need to keep working. Of course, we need to drive better lithography. Don't slow down. But I think the question for us is, do we have the right ambitions to go utilize this technology in front of us? We at Apple are not concerned about the talk of a slowing semiconductor industry. Not the case at all. We think the potential is huge. We believe strongly in both the cloud side, but the future will be a lot of on-device processing. We believe this is the best way to deliver great features without sacrificing the responsiveness and the privacy and the security. We see in our brand new A11 Bionic chip, which is made right here at TSMC, every time somebody takes a photo, there's over 100 billion operations. That's just mind-boggling. Single photo, over 100 billion operations. The potential is limitless. We put a neural engine on the chip, and I won't repeat some of the things that Jensen shared. We have the same view and vision of the potential of AI to deliver a much safer and efficient autonomous system. We believe in it's already enabled. The neural engine on our chip has already enabled Face ID, processed locally, and so we view that the next 10 years is about the ambition to do what Simon's daughter is asking for, to make life better. And probably one of the most significant examples of this is our opportunity to use transistor technology advances and power scaling to revolutionize health care. We think the industry is ripe for change. We think there's tremendous potential to do on-device computing, to do cloud computing as well, and to take that learning and through machine learning, deep learning, and ultimately artificial intelligence, change the way healthcare is delivered. And we can't think of anything more significant than this. So I think the question in front of us is, do we have the right ambitions, and can we go do this? And there is no such thing as autonomous innovation. Human beings dream it, human beings drive it, and sure, we'll have deep learning, but there's not autonomous innovation. So it's up to us, this generation, over the next 10 years, to take advantage of what is in front of us on the silicon world. We at Apple are really inspired. For those of us who started many years ago on a green monochrome computer screen, we're super inspired with the state we're in. And I'll just say this: if in the next 10 years, from a society standpoint, we just do a few gee whiz things like flying car kind of dreams, and then the rest of the time we're using the faster chips to do the same things we're doing faster, we will have squandered one of the biggest opportunities in front of us. I think we're at an inflection point, much like my colleagues, with on-device computing coupled with the potential of AI to really, really change the world. And we couldn't be more excited about it at Apple. and thank you for your time.
Thank you. Thank you, Jeff. I don't think coffee is ready yet, is it? Yes. It is? Yes. All right. We originally were going to take the coffee break at 3:40, 20-minute coffee break, but and we're going to have the mutual dialogue and the questions from the audience after that. So let us take the coffee break now, and let's come back. It's 3:03 now, so let's be back at 3:25. 3:25.
Ladies and gentlemen, may I remind you that you have question forms inside your program. If you have any questions for our panelists, please place them inside the tray. Let me repeat myself one more time. There are question forms inside the program. If you have any questions for our panelists, please write your questions down on the question form, place them on the trays, on the table, and our staff will be coming by to collect them now. Thank you. Ladies and gentlemen, our next item, the panel discussion and Q&A, will begin shortly. Please take this time to find your way back to your seats, and the panel will resume shortly. Thank you. Ladies, hello. Okay. Ladies and gentlemen, our event is about to begin shortly. Please take your seats. Ladies and gentlemen, our panel is about to resume. Please take your seats. Okay.
Yeah, good. Yeah, would everybody please sit down and close the door, please. So we resume our panel discussion. First, I want to ask the panelists, do you have questions for each other? No questions for each other. All right, then I will start. Actually, I have a few questions for you, but I look at this pile of audience's questions. There are enough of them to keep all of us busy the rest of the afternoon, the rest of the session. So I will just start with the audience's questions. There are quite a few questions about AI. The first one, is, when will AI be ready to predict next 10 years in semiconductors? Well, Jensen, you want to take a stab at that?
Everything I said today was predicted by an AI.
Everything you said today was what?
Was predicted by an AI. Artificially intelligent. That's me.
So you haven't given an answer.
Look, there are two types of AIs, and there's surely more categories than that. But an easy frame of mind is there are specialized AIs that are designed to do one specific skill. Like, for example, the ability to recognize images, the ability to recognize speech, translate speech, have a conversation with you, be able to predict stock price. Those kind of AIs are highly specialized. And I think that over the course of the next 10 years, we're going to find that specialized AIs, radiologists, AI radiologists that are reading CT scans, over the next 10 years, specialized AIs will surely achieve superhuman levels. But the other form of AI, which is general AI, I think, first of all, we don't even really understand how intelligence really works at the general level. So general level AI, what is otherwise known as artificial general intelligence, there's no evidence that anybody has a real understanding of how to get there anytime soon. Okay, so.
Actually, I can answer the question. Nobody asked me, you know. But I will answer the question. And I don't, on this point, the next 10 years in semiconductors, I think by that, I think the questioner is asking the market the next 10 years. And I don't quite agree with, I think it was Hock that said that it's just, you know, GDP kind of growth. You know. I think that the semiconductor market will grow 200 to 300 basis points more than the world GDP. That's my answer. 200 to 300 basis points more than the world GDP. Keep in mind, world GDP now is only 2.5 to 3%. Good year gets up to 3%. Not a good year like this year. It's not a particularly good year. 2.5%. And my prediction for the semiconductor market in the next 10 years is that it will grow at 4.5 to 5.5 point, you know, 4.5 to 5.5% compounded annual average.
CC, that's your performance plan. Just got set.
No, our performance plan is far better, far more than that. Our performance plan, incidentally, is 5 to 10% annual growth. Yeah. Okay. Next question from the audience. Again, AI. And this one is from Bill Lu, who is an analyst of UBS. How is the trend for AI chips? How is the trend for AI chips play out? I'm reading it. Would it stay discrete, or does it get integrated into an SoC, like GPU, DSP in the apps process? Well, Bill Lu, you're here, aren't you? Why don't you stand up and ask the question yourself, okay? Yeah. Is he here? Yeah, give him a microphone and let him answer. I mean, what you wrote down is ungrammatical, you know. So.
Hi, I'm sorry about the grammar and the handwriting. But the question, I think, is fairly simple. If you look at AI chips versus what we've seen previously, for example, in the PC, we had the math code processor at one point. Eventually got integrated into the CPU. And then if you look at an apps processor, it's a lot more than the CPU. It integrates the GPU and integrates the DSP and a lot of other things. So longer term, do we think that the AI processor stays discrete, or does it get integrated? Why and why not? Thanks.
You want to take a crack at that also, Jensen?
Sure. First, Bill, it takes a lot of courage to stand up after that question formulated that way. I would have sat down. I would have. There are three markets. I would say that there are three markets for AI from a chip perspective. There's the first market, which is developing the AI network, and there basically what you're doing is the deep learning network, the deep network, is trying to guess what the right answer is, and every time it guesses at the answer, it starts out by guessing at the answer, and every time it guesses it wrong, there's a process that computes the error back to the beginning. So it changes all the neurons. It changes all the synapses, if you will. They call them weights and activation layers. And it would do this trillions and trillions and trillions and trillions of times until eventually, after it's repeated itself so many times, eventually the weights and the activation layers are able to guess the output. Okay, whatever you show it a picture of Morris, and it says Morris. It doesn't even. It's so diverse that you could show it a picture of Morris when he was 55, and now it'll still guess that it's Morris. So this network is very robust, it's very diverse, and it takes a long time to train. In that particular situation, the number of transistors, for example, that's in a GPU for training, call it 100 billion transistors to every 6 billion or so CPU transistors. So it's not sensible to integrate 100 billion transistors and all of the memory that it's connected to, because it needs so much bandwidth, into the CPU. And so in that particular case, for training systems, I think discrete is likely the right answer. Then there's the second category of neural net processing. And I would say that that's the category of autonomous machines. Once you've developed the neural network, you apply it into a machine, and that machine could be a self-driving car. That machine could be an autonomous machine like an iPhone. That machine could be a robot. And in those particular cases, the neural network processing is quite intensive. And so I think that you'll find that there are some that are integrated and some that are discrete. But it's very clear that autonomous machines will see a new type of processor. We're developing a new processor. It's called Xavier. We're in the process of taping it out to TSMC right now. And it's a new class of processor that takes real-time sensor input of all different types, fuses them all together, and it does parallel computing, CPU processing, as well as neural processing, all at the same time. And so in those cases, it could be discrete, it could be integrated. And then the third class I would characterize as IoTs. These are Fitbits, these are thermostats, pressure sensors, vibration sensors. They're sensors of all kinds. And I would think that Analog Devices, Vincent, you guys have tons and tons of these sensors, and they're going to have these neural network processors connected to them, and they're all going to be completely integrated. There's going to be there'll be a trillion of these sensors. There'll be, Vince is going to sell these things like dust. It's going to be literally everywhere. Every vending machine, every elevator, every coffee pot, every pair of tennis shoes, every watch, everything that you wear will have some kind of an IoT device on it. And a little tiny neural network, and in that case, will be integrated. There'll be hundreds of millions of autonomous machines. There'll be tens of millions of training systems and inferencing systems, and there'll be trillions of these IoT devices. And so that's kind of the way you got to think about it, depending on application.
Anyone else wants to add to what Jensen said?
Yeah, maybe if I could kind of give the real world in view, the physical world into the world of digital. Our sense is that artificial intelligence will be pervasive at the cloud and the GPU, CPU, but also many of the things we're starting to plan and do now at the sensor level, as Jensen said, will have some level of artificial intelligence or machine learning right down at the sensor itself. So the partitioning of AI from our perspective will actually start at the sensor all the way to the cloud.
Steve?
Well, same view. I think if you looked at it as a continuum from kind of the cloud here, very, very specialized, a huge amount of processing moving toward the edge of the internet coming this direction. Tends to be more integrated moving that direction, tends to be less integrated moving this direction. But I think, at least for us, we tend to look at it as I think there's going to be a lot more computing closer to where the data actually is, so even closer to the sensor. And I think that's going to be a big opportunity for people in this room, actually.
Simon, anything?
Yeah, I think, as Jensen said, there are going to be a very wide range of applications. There are a ton of algorithms. There are a ton of algorithms yet to be discovered, tons of different ways to utilize machine learning algorithms. Some of those are going to need small chips with a bit of acceleration. Some will just probably run on a CPU, as bad as they are at doing these things. And, at the other end of the spectrum, you've got, enormous dedicated processors that are there for training the networks themselves. So, I think the more that industry scientists, engineers get to play around with this technology, the more use cases there will be, and the broader range of implementations of machine learning and AI we will see. Some will be completely integrated, some will be standalone.
Thank you. The next question is also about AI, but it's a different nature. It's from Paul Schrock. Paul is a consultant. Actually, he works for us. At least partially works for us. He helps us to assess our customers' opinion of us every year. And in fact, just this weekend, I finished reading, or at least leafing through, 2 big volumes that he has just submitted to me. Every time I mean, I do that. I read his reports every year, in addition to listening to his verbal reports. And every time I can help, every time I read those reports, I can't help getting the feeling like the Irish, you know. No matter how hard you try, the world does not like you. Anyway, Paul Schock is in the audience, and his question is, what responsibility do we, as technology providers, have to ensure that AI and deep learning does not end in the nightmare scenario? Let me ask Jeff. Jeff, would you take a crack at this?
What's that?
Speaking of nightmare scenarios.
You know, there've been a few bombastic statements about AI recently, and I think it's important. We throw around terms like AI, like the previous question is, where will the AI be and which chips? Is it in the data center? Is it in... And I think it's important to define AI a little bit more and decide what we're talking about together. The fear of the future, I think, is that you read about, is that somehow machines will take over and start thinking, and I think that is a long ways off. My personal opinion, that's a long ways off. The very AI brilliance that, what we would call brilliance in the game strategy of beating Go, or playing the game Go and winning, you can't take that same learning and play a simple game like tic-tac-toe and win. And so I think we're a long ways off before we're able to do that kind of human thinking. When it comes to, as Jensen said, when it comes to specialized deep learning, I think that's going to open up all kinds of opportunities, and I think most of those are not dangerous. I think the things that we need to guard against when you're dealing with large amounts of data, which are required to do this type of learning, is really around the privacy and the security of that data. And so the future I worry about, I don't worry about in any time in the next couple of decades machines starting to think and taking over the world like you've read about recently. The thing that I think is a real threat is the risk on privacy and security, and that's one of the reasons we as an industry have to be really, really smart about what we do. And it's one of the reasons I mentioned earlier, the significance of so much of this being on device, because I think that provides the greatest level of protection for the individual.
Anybody wants to add to that? Yeah. Peter.
Yeah, of course I'm not an expert on artificial intelligence. The only thing, when that question is being asked a lot, I'm also on the board of a big pension fund in the Netherlands, and when this issue of artificial intelligence and robotics taking over comes up, we need to realize that the demographics in developed countries are tending towards people having fewer people that are able to create the productivity that we actually need. So we need robotics to take part of that, because I would also say that from a societal point of view, that the big discussion is there inclusion or exclusion. So which people are able to follow this development. That's more a societal question that we need to answer. And as a matter of fact, in the countries that I'm close to, Germany and the Netherlands, there's a big focus on education and making sure that we get a workforce that is able to actually deal with these changes and that we don't create as a big mass of excluded people. And I think so. It is about inclusion. I think that's what we need to also be cognizant of. So. Yeah, I think workforce is one. It's we have full employment effectively in big parts of Europe, screaming for talent. I would welcome some automation, and I would say that automated automation.
Thank you. Actually, on this nightmare scenario issue, recently I have been telling the Taiwan press that maybe the first profession that AI will affect may be the medical profession. Because I look at the major hospitals in Taiwan, and every day, every morning, there are hundreds of people registering. In Taiwan, you go to a hospital, you want to see a doctor, for whatever reason, unless it's an emergency. Emergency, you go to the emergency room. But if it's just an ordinary problem, you have to register. And every morning, before the doctors come to work, hundreds of people will be waiting in the registration room already. And they all register, and then they are called by order of their registration. And most of the ailments are just very ordinary, colds, flus, that kind of things. So what I thought and what I told the Taiwan press is that maybe AI can really diagnose those minor ailments better than the doctors. And therefore, those lines will disappear. And also it will be a relief of the load on the doctors. But also, at the same time, we may not need so many doctors anymore. You have any comment on what I said? Jeff, you are nodding your head. You have any comment?
I think we will always need doctors, but I think we will be able to make greater changes in healthcare and empower both the people and the doctors with this. So I don't think we're going to put doctors out of work, and I don't think you're saying that. But if you think about what doctors do today, most of the doctors that we interact with say they only have a few minutes to see each patient. They have very limited data. It's episodic, and there's a big chance to change that in the future. With the Apple Watch, which has a neural engine on it as well, we're doing more and more. We just announced recently that we're doing a very large study in the United States, and we're going to detect arrhythmias. So the number 2 cause of death worldwide is stroke, and the largest contributor to stroke is AFib, and about half of AFib is asymptomatic, meaning the people who have it don't ever have any symptoms. And with the watch, we've run studies, and we've concluded that we can detect this using what you guys broadly call AI. I would say is closer to machine learning, but doing it on device, looking at the photoplethysmograph. And so we envision a world where way less people are dying from strokes because there are interventions if it's detected. And so I agree with Dr. Chang that one of the biggest promises of this is in the world of medicine. And rather than getting rid of all the doctors, I think it empowers the doctors to start having discussions about how to prevent issues from happening instead of just seeing patients after they do happen.
Yes, well, actually, I did not say that we will not need so many doctors anymore, but I did say that we will not need so many ordinary doctors anymore. And what I meant, but did not say, was that we do not need so many mediocre doctors anymore. And, you know, I did not use the word mediocre, but I used the word ordinary. We did not need so many ordinary doctors anymore. But still, I got absolute deafening silence from the medical field. Well, anyway, but I still think that
Morris, one of the largest costs in a hospital is the radiology department, and they're so overworked with the number of scans that are being taken and the number of images that they have to study that they're outsourcing it to the lowest bidder, and they're doing this in droves, and this is just a perfect example of something that deep learning and AI can help to reduce the burden on. And not only will it increase the effectiveness of the diagnosis and the early detections, it'll also dramatically reduce the cost and burden to the hospitals. It's been some time, but I think that between the pressure on the hospitals and also the research radiologists' belief that deep learning is really going to make a big difference, there's just a huge movement in the healthcare industry to automate radiology. So I think that's a really good direction.
Thank you. Hock, yeah. Mm-hmm.
I'm just curious, Morris, how do you sue, particularly in the U.S., an AI chip for malpractice?
That is a problem, I think. Yes. Yeah. So, I'm a little worried about that. Would you sue the maker of the AI chip? Would you sue the designer of the AI chip? Would you sue the user of the AI chip? Yeah.
Probably a process issue.
Huh? Well, Steve, you want to say something about this? You're much better versed on legal matters than I am. Okay? I'm sorry. I mean that as a compliment. Say something about it? No.
He might be deposed later.
I'm going to hide behind privilege on that one.
All right. Now, I was getting to Hock anyway. Hock. Here's a question from Randy Abrams, who is an analyst with Credit Suisse. His question is, in an industry, as Hock Tan mentioned, cloud system companies vertically integrating into silicon and IP. Where are the best opportunities for the chip vendors to create value for these cloud companies and avoid being cannibalized? Hock? You want me to repeat the question?
If you don't mind, just the last part.
Yeah, his question is, if the cloud and the system companies are vertically integrating into silicon and IP, then where are the best opportunities for the chip vendors, including you, okay? Where are the best, including you and us, of course? Where are the best opportunities for the chip vendors to create value for these cloud companies and avoid being cannibalized?
The ultimate defense, to the extent there are prevailing laws that allow you to do that, is really intellectual property. Intellectual property know-how, intellectual property laws. It's really the last line of defense for the chip companies, because under my scenario, at the end of the day, what a chip company like Broadcom does can be done by cloud companies drawing on talent out there who are knowledgeable in the specific areas they are in. For that matter, OEM companies can do likewise. So the only real defense at the end of the day is fundamental capabilities in chip design, which relates to IP. The other best defense, as I pointed out in expanding this question and that I mentioned, is financials, which is it has to be built on silicon. Silicon takes a lot of financial resource to make happen. And to be honest, I think at the end of the day, then the chip company may end up, if they want to stem the reach down the ecosystem stack by cloud guys or OEMs, is really to get back full circle into making chips themselves.
Thank you. Anyone wants to add to that? Yeah, Steve?
Maybe one thing. I think if you can find problems that are bigger than what the cloud companies will do by themselves, for example, something that maybe creates an entire industry that couldn't be done just by one company, those are interesting opportunities to work on. Things like privacy, I would say all of the things like 5G that are just large industry kind of fundamentals, they tend to provide opportunities that are bigger than what any individual company may be interested in and of themselves. I think if you're just looking for things that, hey, I have an advantage because of my size or whatever, it's very difficult to do that with a company that has such investment R&D focus. So you really want to try to get into something that is changing before anyone else is in it, and which is essentially just saying, I think innovation at tremendous scale is really where I think the big opportunities are. And we talked about a couple of them. I think privacy is one, security, authentication of data. If you don't have those things at an ecosystem level, the industry won't develop, and then therefore those cloud companies won't develop services to take advantage of it. And I think that's some of the things that the people in this room do well.
Thank you, Steve. Yeah. Anyone else?
Well, some of the things that are difficult to replace and unnecessary to are platform providers. I think, for example, 5G at some level is a platform for the whole industry. ARM is a platform for the whole industry. If you create a platform by which large ecosystems depend on, it's difficult to replace. If you have large scale in doing something, and the scale is so great and the velocity so high that no single OEM, no matter even if it's a cloud company, could afford to keep up with it, it's easier and more economic for them to buy yours. However, if your business is based on products and features and benefits, I think those are highly competitive, and it's easy to be integrated, and your features and benefits are no better than somebody else's features and benefits in the final analysis when it's integrated into a large system. And so I think those are difficult to defend. But if you have a platform, if you have a large scale, or on the other hand, if you make 1 trillion little things, those are difficult to replace.
Thank you. The next question is about demand, semiconductor demand, semiconductor market. It's from Mr. Masao Asami of Ibera Corporation. The question is, where will the most demands come from for semiconductors for next 10 years? Self-driving, IoT, data centers? And the second question is, how do we better serve those demands? Does anybody want to take a crack at it?
Well, I think I'll take a crack, Morris. I think all those areas are ripe, but the one area I think that has been, if you like, a little dormant in terms of the innovation trajectory over the last 20 years or so is industrial automation, robotics, the factory automation, process control. There is a lot of anxiety amongst those customers now to be able to use ubiquitous sensing, to be able to do predictive analysis, predictive maintenance, and so on and so forth. And it's all about, ultimately, these customers wanting to add more value to their own product portfolios, but leverage the technologies that they've been very shy to do for many, many years. And so what we're seeing is a lot more demand for sensing. But I think ultimately, though that class of problem will find it very, very hard to take root if we don't find a way to secure the data right at the sensor. So I think those two things will go hand in glove. I mean, it's well publicized about autonomous driving, what's happening there, and so on and so forth. But my sense is that the initiatives, for example, in China around replacing human capital with machine capital, that's a very, very real class of opportunity and problems to solve.
Anybody else? Yes, Simon. Mm-hmm.
I mean, I think in the near term, IoT is going to drive a lot of volume. And one of the reasons for that is because there exists already today good enough technology to solve a lot of IoT problems. Now, it needs to get better. We need better non-volatile memories. We need to be able to integrate all these different technologies, all the sensors and the digital all together to make it better. But you can do a lot right now with the technologies that exist. So I think that will drive a lot of volume in the near term. I think in the long term, though, the semiconductor content that is going to go into, I wouldn't say cars, but all vehicles to enable truly autonomous driving under all circumstances, there's a long way to go and a lot of R&D required to create all those technologies, but it will ultimately consume an absolute ton of silicon. I think that's going to be a big driver in a kind of 10-year plus time frame.
Thank you, Simon. Speaking on behalf of TSMC now, we do have 4 growth platforms. One is mobile. I think mobile is going to remain a very strong growth platform for semiconductors and therefore for our business, for TSMC business. The second is high-performance computing. And the third is IoT. And the fourth is automotive. These are the 4 growth platforms that TSMC has right now. Anyone wants to add?
Well, some of I agree with those 4, and IoT is super exciting because in some way it's sensing IoT, these intelligent machines. We used to have computers. In the future, we're going to have computers that are able to perform autonomous things all by themselves. And so most of our computers today, we either type into or hold on in our hands, but we're going to have intelligent machines everywhere. We're going to have intelligent buildings. We're going to have intelligent factories, Factories are going to be AIs. Factories are going to run robots that are going to build other robots. And all of these robots are going to be autonomous. The entire warehouses will be autonomous, and warehouses will become big AIs. And today, warehouses are non-markets for us. Robots are small markets for us. And in the future, these robots will have dozens of computers inside, not just one ECU that's mimicking the motion that somebody else had programmed. And so I think all of these new intelligent machine opportunities made possible by AI are brand new opportunities for us, and it didn't exist before, and it's starting from zero, which is the exciting part.
The next question, we really cannot escape Moore's law in any semiconductor meeting. So the next question is about Moore's law. What will happen after maximum of Moore's law? When would that be? What's TSMC's strategy or view? And I don't want to answer the last question, okay? But the first two questions are, what will happen after maximum of Moore's law? And when will that be? Peter, you want to take a crack at that?
Well,
at least the second one. At least the second one. Yeah.
I wouldn't dare to answer the other one. No, I always say when people ask me Moore's law, what's Moore's law? It's an empirical law of economics. Huh? I mean, it's making sure that the cost per function keeps going down. So we either create more functions, then we decrease cost. But it's either or. I think from a lithography, from a patterning or a scaling point of view, I think we have a clear vision, a roadmap that will bring us to 2030 and further. And beyond that, I don't know. And it reminds me when I joined the company, and Martin van der Brink, my co-president and good friend, he interviewed me and said, "Peter, we want you to come." I said, "Martin, I have a decent job, so why would I join? Yeah, because there's Moore's law. This shrink keeps. There must be an end to it." So he said, "Listen, Moore's law stops when we run out of ideas, and we have still a lot of ideas left." And he says, "So another 15 years, if you have the patience, you just join." I asked him the same question today. He gives me the same answer. So this 15 years that beyond 2030 that we're seeing from a lithography point of view. But like I said in my talk also, I think it is more and more important that we connect the dots. Yeah? That we connect the dots. It's the complexity is increasing exponentially. It actually means that we need to look at everything that adds to keep the cost under control, because it is an empirical law of economics. Yeah? And I think this is where this collaboration over the next 10 years needs to take different forms. Yeah? And don't talk about traditional M&A. Because there's a legislative barrier, I think, but it is about how do you create partnerships where you're willing to share the risks and the rewards. I think that's going to open new venues for the key players in this industry, and I think we will be able to do that. We've shown that we can do it. This is an industry that has massive earnings power, $300 billion of EBIT every year. I think there is massive knowledge and technology. But we do need to step up the cooperation and the collaborative models, and we'll make this happen.
Actually, Moore's law is no longer valid because Moore's law has a time element in it. Moore's law, the original version, and the original version of Moore's law was doubling of transistor density every 18 to 24 months, doubling of transistor density every 18, 24 months. And the doubling of density is continuing, but not every 18 to 20 months. That's why I said that the time element has already disappeared. So that makes the original version of Moore's law invalid now. Yeah. But the density doubling is going to continue. And according to the answer that Peter just gave, they have planned till all the way to 2030. You know. And that's like 13 years more. Now, in my opinion, I think that the economic feasibility of density doubling will be tested first. So before it's technically unfeasible to double the density, the economic viability will be tested first. And that may come before 2030. In fact, I think it may come, our plan is right now, TSMC assumption right now is that 2025, 5 years more conservative than what Peter just said. 2025, we are expecting that we'll continue to work on density doubling for another 8 years. I don't know whether, well, first of all, the future chairman and CEO of TSMC are sitting right here. If you disagree with me, please stand up and say that. Mark says he doesn't disagree with me. You see, I don't even see CC. For real. 2025, yeah. Yeah. All right. As to what will happen after the maximum Moore's law, Hock, I think you said something about that earlier, didn't you?
I don't recall that.
I think you said things, more than more. You said more than more, yeah.
Well, I think we're reaching, well, it will be still a while away, but I think at some point we'll go full circle into a situation where, the service providers, clouds, everything else would start to vertically integrate down to silicon. And at that point, I think it's architecture, systems, and software, as much as hardware, silicon.
Thank you, Hock. Here's another question. As limits is from Mr. Thayer, Mr. or Ms. Thayer, T-A-H-E-R, from Open Silicon. The question is, as limits of physics come into play, does the panel feel that organic molecules could play an important role in increasing the density of data storage in the future? Does anybody want to answer the question? I don't know enough about organic molecules to answer the question.
Organic molecules?
Do you? Yeah.
No idea what he's talking about.
Neither do I, neither. Oh, DNA.
Oh.
He says DNA, parenthesis DNA. Does the panel feel that the DNA could play an important role in increasing the density of data storage in the future? If anybody can answer the question, I think it would probably be some technologist.
My guess, Dr. Chang, is the question was along DNA with the level of deep sequencing and all of the data and storage and all that. That's what the genesis of the question was.
I see. Now, do you have an answer for the question there?
I was just trying to help.
I know you are.
You know what? You know what's really, really interesting is when you look at the genome and you look at all of the sequencing of the genome, the most efficient way to store this data is to store the sample itself, because the way human nature has done it is more efficient than we can project in memory for the next 10 years. So you're better off to hold the sample until the sequencing versus sequence and store all the data. The way nature has done it is better than the technology, at least for the next several years.
Thank you. Thank you. Thank you, Jeff. Here's a question about technology again. It says it's for me and for Peter Wennink. Do you see founding size shrinking through equipment optimization with technology advancements of future? It says it's founding. What is founding size? Is Mr. Jahangir here? Yeah. Would you give him a microphone? And what was your question? Yeah.
It was foundry size shrinking.
Foundry size shrinking. Foundry size is not shrinking.
That's correct. So the question is, with the technology advancements, do you see a vision, technology development in the next 10 years can bring to the foundry manufacturing of wafers, can shrink instead of mega foundries or giga foundries, we can produce more devices in smaller area?
In smaller physical area, you mean smaller plant, is that right? In other words, can we increase the equipment, it says equipment optimization, can we make the equipment more and more productive so that we'll need less equipment? I think that's the question. And well, I have an answer to that. I don't think so, but Peter, you go ahead.
Well, as a matter of fact, we've over time sold fewer and fewer machines at higher and higher prices, as you know. So, it's just true. But effectively, it comes back to what we said earlier. It has to be able to, keep reducing the cost per transistor per bit, or how do you want to call it? I mean, there's, and I do agree with you, Morris, that Moore's law will stop sooner through economics than through physics. And that is continuously a challenge. It's always been a challenge. Currently what we have in front of us, and it's just part of the total equation, is lithography, because like I said earlier, it is the combination of lithography with our peers in the industry that provide the material knowledge, that provide the deposition tool, the etchers, and everything that we need. And we need to collaborate very closely, in a very transparent manner with our customers to really understand what their needs are, so that we can work together to solve those, I would say, technical, but also the economical issues. And I think that is the biggest. From a technical point of view, we will shrink. We have our research done, and it's pretty accurate that we are able with high NA to further keep shrinking. That's not the point. The point is, can we do it economically? And I think that's going to determine how big or small, but I think big, the industry is going to be. And like I said, there's many of these elements that need to come together, and the different types of scaling, architectural scaling, device scaling, that all needs to work together. So it's extremely difficult to give an answer on when does that end. But economics are the brick wall. I do agree.
Thank you, Peter. Now, I have the last question. I like to close this session in about 5 minutes, and so I will save the last question for myself. And the question is principally one of Jeff, I think. Do you see a lot of AI in mobile devices? Just phones, phones or other mobile devices. Do you see a lot of AI in a lot of deep learning AI in the mobile devices?
Yes, I do. Yes.
That's it?
We talked about some of this earlier, but we do. We think that the frameworks that we've got. We talked about the neural engines that we've put already in the phone and the watch, and given a few examples. But we do view that as a huge piece of the future. And we view these frameworks will allow developers to create apps that will do more and more in this space. And so we think the phone is a major platform for the future. Not exclusively. Some pieces will be done data centers, some pieces will be done on device, but we're already doing AI in the broader sense of the word AI, not the machines thinking for themselves version of AI.
Thank you, Jeff. Since Jeff only took a couple minutes, let me ask Vince a question. Vince, analog devices is really in standard products, isn't that right?
It very much depends on the market, Morris. I think where we standardize would be, or build standard products would be in very fragmented applications, number of customers, but clearly as a company we've been moving more heavily into more application-specific custom products where the market can justify it, and there's a very high concentration of the revenue in few customers. So it very much depends. But
how much of your revenue is in what you call standard products, and how much in the other one, in the other kind?
Well, with the addition of LTC over the past number of months, the amount of standard products in the portfolio has increased. So that was LT was a very, very standard product play. And we, all the time we are trying to balance the investment between doing more standard product, more open market type things versus more customization. But clearly the trend at ADI has been more customization over the past 10 years.
All right, so let me get to my question then. One usually associates low profit margin with standard products. How does analog devices get such a high profit margin with so many standard products?
It's a great industry secret. I think it depends very much on the market. Not all markets produce the same economics for ADI. So it very much depends on the type of product and the type of market in which you're playing. So clearly the fragmented markets, I would say, offer more attractive margin structures, and the more concentrated markets, the buyer has some very, very strong power, so the seller has to do a lot more bargaining.
Thank you. And now we end this panel session, and I want to thank all the panelists. And I thank you for participating, and you have been a great panel. Thank you.
Thank you, Dr. Chang, and distinguished panelists for a very insightful discussion. Please remain on stage for the group photo. If you could help us by gathering at the front of the stage, and our photographers will be coming in shortly to take your photos. Thank you very much. Okay. Thank you, everyone. If you would please join me again in thanking Dr. Chang and the panelists. We will now have a short break before dinner. If you could return to your seats in around before 5 o'clock. Thank you.